So this is the minimum energy we need to collide and react. See that the shaded area, that number of particles, they do have enough energy to form an effective collision. And if I can have more collisions per time, then I can have a faster reaction rate. There are three things in the collision theory that you need to memorize. One of them is that for particles to react, they must collide. And I know that's intuitively obvious, but we think about particles three-dimensionally when we talk about collisions. And normally we look at reactions written on paper and we forget that they're actual particles that have to bump into each other to react. The second thing is when they do bump into each other and collide, they must have the correct orientation. So in other words, the oxygen end of this molecule is not going to do it. It has to be the carbon end bumping into the oxygen for a proper orientation. The third thing is when they collide, they have to have sufficient energy. And you've probably heard of activation energy, and that would be E subscript A. So this is the minimum energy we need to collide and react. Okay, so let me show you this distribution. You have seen this before. So remember the principle that in a sample, not all the particles have the same energy. So let's say we were at T1, some temperature. This is a distribution of particles. And the guys on the left with lower energy are moving slower. Okay, and as we go to the right, they're moving faster speed. So some small number of particles have a high speed. And the activation energy for this reaction is this number. And we can look at the distribution and see that the shaded area, that number of particles, they do have enough energy to form an effective collision and actually react. Well, let's heat this sample up. What happens to our curve? Well, if T2, we'll go to T2 here, is greater than T1, the curve is a little bit flatter and it shifts to the right. And so what we have is a higher average temperature or average kinetic energy. And we actually, at our activation energy, now this time we have more particles here. We have a greater number of particles that have enough energy to react. And that makes total sense, right? You know that reactions are very sensitive to temperature. So the higher the temperature, the greater the number of particles that have enough energy to form an effective collision and actually react. So let's talk about collisions and how can we increase the rate. That is a key word in this area of study. The rate of reaction is how fast reactions occur. So there's three things you can do to increase the rate. The first one is to increase the concentration. So if I added some particles to this box, we have more particles in the box, and so we have a greater chance of collisions. So to increase the rate of reaction, what we have to do is increase the number or the rate of collisions. If I can have more collisions per time, then I can have a faster reaction rate. So more particles in the box, then more collisions. Okay, it makes total sense. The second one is to increase the temperature. Now remember, temperature is proportional to kinetic energy, and kinetic energy is, do you remember, 1/2 mv squared? That is the velocity. Okay, so if we want to increase temperature, we increase kinetic energy, and we will increase, well, that's the mass, that's not going to do it. We'll increase the velocity. So higher temperature, faster moving particles, so we will have more collisions because they're moving faster. All right, and with more energy, more speed. And then the last thing is a catalyst, okay? And a catalyst doesn't enter into the reaction, but it does make it go faster. A catalyst will lower the activation energy, and that's how a catalyst will increase the rate of reaction.